Welcome back to the deep dive. Today, we are going deep. I mean, really deep into the source code of modern physics.
We're tackling Albert Einstein's 1905 paper on the electrodynamics of moving bodies.
And our mission here is to get past the usual summaries, the stuff you see in documentaries. We're going straight into the math.
Exactly. We want to understand the actual, the logical steps and the precise definitions he used to build special relativity from the ground up. This is really about the mechanics of the theory.
Right. And what's so fascinating is that he doesn't start with some grand cosmic vision. He starts with a really practical problem, a kind of asymmetry in the physics of his time.
It's a very elegant starting point, and it comes from Maxwell's electrodynamics. It's all about the interaction between a magnet and a conductor.
Okay, so let's walk through it. There are two scenarios with the exact same relative motion.
Right. Scenario one. You got a magnet, and it's moving. The conductor's just sitting there at rest. Because the magnetic field is changing where the conductor is, Maxwell's equations say an electric field gets created. And that electric field pushes the electrons. It creates a current.
Simple enough. Now scenario two.
Now we flip it. The magnet is at rest, and the conductor is moving towards it at the exact same speed as before.
So the relative motion is identical.
Identical, but the explanation is completely different. In this case, there's no changing magnetic field at the magnet, so no electric field is created.
So where does the current come from?
It comes from something called an electromotive force, which arises because the charges in the conductor are moving through a magnetic field. That force drives the current.
Wait, so the end result, the current you measure, is exactly the same in both cases?
Exactly the same. But the reason for it, the theoretical explanation, it totally changes based on what you decide to call stationary.
It just feels wrong, doesn't it? The physics shouldn't depend on your point of view like that.
That's precisely what bothered Einstein. It felt arbitrary. That and the fact that for years, experiments like the Michelson-Morley experiment had failed again and again to find any evidence of the Earth moving through this supposed ether, this absolute stationary space.
So he just decided to get rid of it.
He made it unnecessary. And he did that by proposing just two postulates, the twin pillars of the whole theory.
And the first one is the principle of relativity itself.
Yes. It says that the laws of physics, not just mechanics, but and this is key, electrodynamics too, are the same for all observers in uniform motion.
So no special or at-rest reference frame. The physics is the same for everyone who isn't accelerating.
Right. And the second one is the real bombshell.
The speed of light.
The principle of the constancy of light velocity. Light in a vacuum always travels at a specific speed, c, and that speed is the same for everyone, no matter how fast the source of the light is moving.
And that simple idea just breaks everything, doesn't it? It completely upends the Newtonian universe. Because if c is constant for me standing still and for you flying past me at half the speed of light,
then our measurements of distance and time have to be different. They must be.
So how does he prove this? How does he build a new system from these two ideas?
He starts with the most fundamental thing he can, the definition of time itself. Specifically, the definition of two events happening simultaneously.
The clock synchronization thought experiment.
Exactly. It's the absolute foundation of the kinematics. Imagine you're in a stationary system, we'll call it K. You have two clocks, one at point A and one at point B.
And you need to make sure they're showing the exact same time.
Right. So you send a light beam from A to B. It leaves A at time TA, hits a mirror at B at time TAB, and reflects back, arriving at A at time TAs.
Okay.
You define the clock as being synchronized if the time it took to go from A to B is the same as the time it took to go from B to A.
So TB minus TA equals TA minus T days. It's perfectly symmetrical.
Perfectly. This definition also locks in the value of c, the speed of light. It's just the total distance, 2 AD baudr, divided by the total time, TAA.
Now for the twist. We apply this definition to a moving system.
Yes. Let's imagine a rigid rod with clocks at both ends, A and B. This whole rod is moving at a velocity, v, relative to our stationary system, k.
And from our stationary perspective, we say, okay, those two clocks on the moving rod are synchronized according to our definition.
But now let's analyze what's happening from inside that moving frame. A light signal is sent from A to B along the rod. From our stationary perspective, B is moving away from the light signal as it travels.
So the light has to catch up to it.
Exactly. The effective speed is c minus v. So the time it takes is the rod's length, let's call it 3ABD, divided by CdVB.
Then on the way back, from B to A.
Well, now A is moving towards the returning light signal.
So it's closing the distance faster.
Right. The effective speed is now c plus v. So the time for the return trip is 3AB divided by Zickel-Blotzen plus v.
So the time to go from A to B is not the same as the time to go from B to A.
Not at all. One has sine v of others in the denominator, the other has sine plus v. They are not equal.
And this is the moment. This is where absolute time just dies.
It's gone. Because for the observers moving with the rod, they just violated the very definition of synchronicity. Two events that we in the stationary frame declared to be simultaneous are not simultaneous for them.
Simultaneity is relative. Wow.
And once you accept that,
Yeah.
you realize you need a new set of equations to translate between these different points of view. You need a new way to connect space and time.
The Lorentz transformation.
Lorentz transformations. The goal is to find equations that connect the coordinates of the stationary system, yzt2, to the coordinates of the moving system, which he calls ia, eta, zeta, tau.
Okay.
He requires the transformation to be linear, because space and time are uniform. And when you apply the two postulates, especially the constant speed of light, the math just sort of falls into place.
And this is where that famous factor beta comes from, right?
It emerges naturally from the derivation. Beta, which is frat 1 v2c2. This little factor is the mathematical heart of relativity.
It's the thing that measures how different the world looks at high speeds.
Precisely. And after ensuring that the transformation is symmetrical, that the view from the moving frame back to the stationary one uses the same rules, he arrives at the final equations.
Let's look at them. The coordinates perpendicular to the motion, y and z, are unchanged. So data and zeta are a theta via.
Correct. No surprises there. But the coordinate along the direction of motion, x eta, becomes beta vtt.
Which is kind of like the old Newtonian version, just 6vd, but now it's stretched by this beta factor.
Right. But the truly revolutionary part is the equation for time. Time in the moving frame, tech zeta, is equal to beta vx zeta.
And that is just mind-bending. The time in the moving frame, Terra doesn't just depend on the time, $p in our frame, it also depends on the position, 6tel.
That little Cx(c22) term is everything. It's the mathematical signature of the relativity of simultaneity. It explicitly mixes space and time into a single fabric. Time at one point is literally different from time at another point because of this blending.
It's the Rosetta Stone for space-time. Once you have that, all the famous consequences must follow, right? Let's start with objects themselves. Length contraction.
Okay, so imagine a perfect sphere with radius $3 just sitting at rest in the moving frame K. Now we, in the stationary frame K, want to measure its dimensions.
The y and z dimensions, perpendicular to the motion, would be unchanged. They'd still be r.
Still are. But the x dimension, the one along the direction of motion, gets transformed. And because of that beta factor, it appears shorter. The sphere to us looks like an ellipsoid. It's squashed.
By how much?
It's shortened by a factor of 1 over beta, or square root of v2c2.
So as you get closer to the speed of light, that square root gets closer to 0. The paper actually says moving objects would shrivel into plane figures.
The math is uncompromising. An object's length isn't a fixed property anymore. It depends on how fast it's moving relative to you.
And the same must be true for time. Time dilation.
Yep. Take a clock sitting at the origin of the moving system. We watch it tick from our stationary frame. We find that its time passes more slowly than our time, $10. The equation is tau or square 1 v2c2.
A moving clock runs slow.
Always. He even calculates the effect for small speeds. He shows it's slow by about 1/2 VTC2 seconds per second. A tiny, tiny amount for everyday speeds, but it's real.
Okay, so space shrinks and time slows. What happens when you try to add velocities? You can't just add them anymore, can you?
No, that would break the speed limit of light. If you're on a train moving at velocity v and you throw a ball forward at velocity w, the total velocity v that I see from the ground isn't just v plus w.
What is it?
The new formula is $v frac v plus w1 plus vw2.
Ah, and that little term on the bottom, the VWC2, that's the key.
That's the relativistic correction. It ensures you can never break the speed limit. You can even try it. Say v is 90% the speed of light, and w is also 90% the speed of light. Classically, that's 1.8 c.
Faster than light.
But with this formula, the answer comes out to be about 0.994 c. Still less than c.
And what if one of the velocities is c? Say you're on a spaceship traveling at c and you turn on a flashlight.
The formula gives you a perfect result. V equals c. The light from your flashlight still moves at c relative to me. The speed of light is absolute.
It all fits together.
And this leads right from kinematics, the description of motion into dynamics, the cause of motion. The last part of the paper deals with what happens to mass and energy.
Right, because if you can't go faster than c, something has to happen when you keep pushing on an object. its inertia must increase.
Exactly. When Einstein transforms Newton's ESPA into his new framework, he finds that mass is no longer a constant. In fact, you get two different kinds of mass, depending on which way you push.
Longitudinal and transverse mass. What's the difference?
Longitudinal mass is the inertia you feel if you push the object in the same direction it's already moving, trying to speed it up. Its formula has a squirt1 VTC2 333 in the denominator.
And transverse.
Transverse mass is the inertia if you push it sideways, perpendicular to its motion,
Yeah.
trying to make it turn. Its formula is a bit different. It has a big 2c, $2 in the denominator. The point is, both of them get larger as the velocity v increases.
And as v gets closer and closer to c.
Both masses approach infinity. It would take an infinite amount of force to accelerate the object any further.
Which connects directly to energy, I assume.
It does. He drives the formula for the kinetic energy, W, needed to get an object up to speed v.
And what does that look like?
The kinetic energy is a W C2 left, squirt E1 V2 C2 whites.
I see that beta factor again right there in the middle.
It's everywhere.
Huh.
And look what happens. As v approaches c, that fraction with the square root, it goes to infinity. The kinetic energy required to reach the speed of light is infinite.
So it's not just a rule, it's a physical barrier built into the fabric of energy and mass.
It is the ultimate speed limit. And the amazing thing about a paper is that he didn't leave it as pure theory. He gave experimentalists things to go out and measure.
Like what?
He derived a precise prediction. If you shoot an electron through electric and magnetic fields, the ratio of how much it's deflected by the magnetic field versus the electric field gives you a direct measurement of its velocity. The ratio is just $5.
So he was saying, here's my theory, and here's exactly how you can go test it.
That's the beauty of it.
Yeah.
It's a completely self-contained logical structure, starting from one small puzzle about magnets and ending with testable predictions about the fundamental nature of mass, energy, space, and time.
It's just staggering. The entire framework of modern physics, all derived from fixing one little asymmetry.
And to leave you with a final thought, let's go back to that time dilation calculation, the one about the moving clock running slow. Einstein himself points out a consequence in the paper. He says if you take two perfectly synchronized clocks, leave one at home, and take the other on a round trip at some constant velocity v, when you return, the traveling clock will be behind the stationary one.
By that tiny amount, the 1/2 B2C/C22 breaths.
A tiny but real amount. He even notes that this means a clock at the Earth's equator, which is moving due to rotation, must run ever so slightly slower than an identical clock placed at one of the poles.
Which is an amazing thought, but seems academic.
But now scale it up. Take that exact same formula derived in 1905 and applied to a GPS satellite. Those satellites are moving at thousands of miles per hour. That V is significant. Their clocks run slower than ours on the ground by a very measurable amount.
And if we didn't correct for it,
If engineers didn't use Einstein's time dilation formula every single second of every day to adjust those satellite clocks, the entire GPS system would fail. Your phone's navigation would be off by miles within a day.
so this intensely mathematical 100-year-old paper is running on our phones right now.
It's the engine of our modern high-speed world. That's the power of getting the math right.